Hello, welcome to this LogicLounge here at TU Wien. So we have Hartmut Neven here, the lead of Quantum AI Lab of Google, and Sarah Kriesche from ORF, the Austrian Broadcast Corporation, and Ö1. Ö1 belongs to ORF.
No, but I'm radio, so we have them walking with folding shirts. So I'm always like that.
And just LogicLounge, that's a format and series that was created by Helmut Veit and Oliver Lehmann at the Vienna Summer of Logic 2016. And since then, we had many iterations, also not only here in Vienna, but also at other continents. And so this is meant to be an informal discussion. So yesterday we had the Vienna Goethe lecture with Hartmut Neven as the speaker, which was more a formal thing in a big lecture hall. But now we have a more intimate setting, and I hope we will have an interesting discussion here.
I take over the microphone. Oh wow, it's really okay. Hello, also from our side, and informal is the word for you also to know. So please join us by raising your hand or come closer if you have any questions, or if you say like, I want to take the chance to really ask the question I've been looking forward to ask for such a long time. I mean, to him, not to me. I hope. We are joined, I prepared many questions, but a little introduction as well, by a researcher whose work has shaped some of the most forward-looking areas in computing. Hartmut Neven is a pioneer in computer vision and quantum information science, and he played a central role, correct me if I'm saying something wrong, in establishing the Quantum Artificial Intelligence Lab. We'll come to that later on. His contributions span machine learning, new computational architectures, and the long-term question of how these systems change our technological horizon. So I'm so honored to be sitting next to you. Please welcome Hartmut Neven. I have the privilege that I knew I would be sitting next to you, so I have a lot of questions prepared. So would be the bad news for all of you. If you have a question, make yourself somehow seen by me, because of course it's about you and the chance to talk to Mr. Neven. But I will do the first question. It's an open one, because in your field, it gets very technological very quickly. And the translation to, okay, how do I communicate that to someone who is not in the field? Is there a worst case question for you where it's like, always this question is coming, and I wish they wouldn't? And on the other hand, is there a question where you are like, why does never ask someone working in quantum, this specific questions? What's your darlings and what's your worst case scenarios when you try to translate your work and the field of your research to a broader audience? And don't forget the microphone.
So I think questions in general have gotten much better over the last year, so there's not that many complaints. Maybe the toughest question is, my younger boy often asks, Dad, for this, wouldn't a quantum computer be so much better? And then there's some specific challenge, like play chess or some other problem you can think of. And then the answer is often disappointing, and I hate to give a disappointing answer because quantum computers are very special tools. So they can do certain tasks much better than classical machines, but the set of tasks is still rather limited. There is a website called the Quantum Algorithm Zoo, and it lists 70 algorithms for which we expect a quantum advantage. And then invariably, people, like my boy, they ask for an area where it's not included in one of these 70 areas where we can have an advantage.
Is science fiction also like one of the recurring questions, because it draws the picture of what quantum would be able to, and can we do that now? AI had this as a passenger in the field too.
Yeah, I think the field overall has very much, we have our heads down and just try to show, look, we can do interesting computations with these new machines. And I see less time being spent on, okay, assuming this all works, which at this point seems rather likely, what would happen in 20 years or 30 years? What would quantum computing then mean?
Today, it was already mentioned, you did a Gödel lecture yesterday, and today was a radio feature about you in Ö1 Journale, Mittagsjournal, in case someone is interested. And there was a term, I didn't know that, and I find it very interesting that they said, like, within Google, you are called the chief optimist, and your department gets reduced to that. I mean, make that happen with researching quantum technology. How come?
Yeah, I think when we started it, these days you have to be much less of an optimist. It becomes, I described it already a few times over the last few days. If you were to visit our lab and you just walk through the corridors and go in the lab and you talk to young engineers, and then you will see they have little doubts that we will not succeed in building a large quantum computer. So there's this palpable sense of optimism all around, but that wasn't always the case. When we started it, I had a lot of pushback and criticism, like very senior engineers at Google coming to me and saying, hey, Hartmut, I think computing is snake oil. I don't think this will ever work. And what can you do? And the obstacles, I mean, it seemed rather unsurmountable. There are still people today, serious scientists, who claim they have sort of almost mathematical proofs that you can't build a quantum computer. Needless to say, I disagree with this, but in light of such challenges, you have to stay optimistic for a while, otherwise it's hard to get yourself up in the morning.
But I think there might be a life lesson there too, because I think everyone is or was in this situation where you have a senior researcher who says, like, yeah, nice what you're doing, but makes no sense at all. And the seniority gives it more power than maybe young you joining there and being optimistic. So the challenge is how to stay optimistic then. Is it the team or the young researchers who say we are more and we're coming, or how you still are state the chief optimist? I have to get used to it, the CO.
I think that there's there's a saying that goes like, if you ask a very senior, accomplished professor whether a certain engineering challenge can be done, and if he says yes, then you can typically trust that indeed it can be done. If they say no, you should be skeptical.
Yeah, I should try not to get so intimidated at work. In your recent work, the quantum echoes algorithm, you claim a verifiable quantum advantage. From your perspective, what makes this result fundamentally different from the 2019 quantum supremacy experiment?
Okay, so this is a bit...
We're getting a bit more technical here, sorry. But raise your hand, make yourself seeable. We're open to your questions, by the way. Get a nod.
So this indeed is a bit more technical to explain. So the 2019 problem where we showed for the first time that a quantum computer could do a computational or a well-defined computational task much faster than a classical computer. That problem is called random circuit sampling. And I can maybe briefly explain what this is. Random circuit is basically, as the word suggests, it's randomly picked operations on your qubits. So in our computers, or a typical quantum computer has 1 and 2 qubit operations. This is a universal set of operations, meaning that any quantum algorithm you can ever dream up with, you can express with these operations. They have a bunch of qubits, in our case, arranged in a 2D grid. And now you apply over time various operations. And you build up a very complicated quantum superposition state. And then you measure the state. And then you get so-called samples. These samples are, if you have, at that time we had 53 qubits. So a sample means you get 53 zeros or ones. So a bit string of length 53. That's one sample. But there are, of course, many possible samples. It's 2 to the 53 samples. That's a very large number. But every time you run your random circuit, you get one of these bit strings. But because there are so many, or I should say this before, so now this random circuit defines a probability distribution. Each bit string is drawn with a slightly different probability. And if you do this for a while, let's say you draw 10 or 1,000 samples, then there are mathematical tests with which you can check that indeed those samples are drawn from probability distribution defined by the superposition state that was your output. Yeah? But you get these samples. And because there are so many samples, you typically never get a sample twice. So if I just do the computation once, you would have no chance to know whether I just made up this bit string of 53 bits or it was really computed by the quantum computer. So that is not easily verifiable or not verifiable on a single run. Versus the quantum echoes algorithm, what this computes, it computes what we call a local observable. It's essentially a measurement you can do on one, or in our case it's typically on one qubit, it could also be a measurement on few qubits. And every time you run it, it should give you the exact same answer. The observable will have a certain value. And this you can essentially check if you had a second quantum computer and you would run it again. It should give you the same result. Yeah, that's for different than the sampling problem. There, if you would have taken a second quantum computer, you would have run it, you would have seen a different bit string. So that's what we mean by verifiable.
I'm looking into the... by the way, is someone in the field of quantum or is thinking about going to that field? No one. Yeah, one. Since you just joined, feel free to ask questions if you have any, or if you want to take your chance, just do what you just did, raise your hand, and we will, he will answer it. I want to come to, I love the name also, but I want to come to Willow. Does it already tell you something about the scalability limits? Because scaling is always a huge question of superconducting qubits, and how far are we today from running a small, fully fault-tolerant algorithm end-to-end, not just a protected memory? And I like Willow because it's so futuresque and it's new.
It's the first, as you see, our seamless planned names to name our processors. The first ones.
Google is good with names anyways, except of Banana One.
Nano Banana. Shall I first answer it? Or?
Answer first and then I see you.
Yeah, so there
Willow.
Some questions combined. So let me ask the second one first. We have always said, chief optimist, from the early days of our project, that by the end of this decade, we will have a feature-complete quantum computer that is a fault-tolerant quantum computer, and it will there's a number that may change a little bit, but we'll have hundreds or possibly thousands of logical qubits. This prediction, I think, still holds. I used to be certain it will be thousands. Now I think maybe more. Hundreds could be more realistic, but that is highly likely that we will get there. And with those machines, you can certainly do useful computations that people would be interested in. Willow is a step on this program. The main achievement with Willow was so actually it's not a main, there are a few important achievements. One is we demonstrated for the first time that quantum error correction works in practice, a key technology for scaling up. We reconfirmed the random sampling, random circuit sampling tasks that we just talked about, and that it would take a huge amount of time classically. For Willow, it became 10 septillion years, so that's 10 to the 25 years on a classical supercomputer to do this task. And you mentioned quantum echoes, so the first verifiable, or actually I like to think of the first useful beyond classical quantum algorithm. So these were all achievements surrounding Willow, but Willow has 100 physical qubits. The machine, by the end of this decade, we wanted to have 1 million or at least a few 100,000 physical qubits. So there is still 3 orders of magnitude, factor 1,000 to go. And yeah, there will be scale-up challenges along the way. And yeah, maybe don't make the answer too long. I can tell you about in a different section what they are.
In the bar. I'm coming to you, so you have a microphone. Hang on.
So we have experiments showing that quantum computing has like a superiority with traditional computing. But do we already know what is doing the heavy lifting? Like what aspect of quantum is it just the superposition, the entanglement? What it really is the difference?
Yeah, you just mentioned it. The entangled superposition states that you can. Actually, yesterday in the Gödel lecture, I sort of assumed everybody knew what a superposition state was, and then when I looked into people's faces, and you don't really know this. And that's of course a key concept. Not sure whether it's worth. Seems like only a few of your quantum people. Should I explain it? So my TED Talk go-to way of explaining quantum superposition is the following way. Actually, normally I do it with coins, but I don't have coins here. So let's look around this room. So we are sitting here in a certain configuration. You sit to the left, and to your right. You sit in the first row. This is what in quantum jargon is called a classical configuration. We can imagine another classical configuration of this room. You and I, we could switch chairs. Now, you could switch a chair or go to a row behind. So we can make many, many configurations. There's actually a combinatorial number. There's a huge amount of different ways how the people in this room can sit on the available chairs. So what a quantum mechanical superposition state is essentially a superposition, sort of the mathematical tool we use to describe a quantum state that contains or is a complex overlay of many, if not all, of these possible configurations. And the amazing thing with the quantum systems is that they simultaneously can be in many of these classical configurations at once. But that is not just a mathematical concept. It must have ontological status, because our algorithms can only be that fast, or our computational advantages can only come because in one clock cycle, I can touch all these configurations at once and do an operation on all these many, many exponentially large number of classical configurations simultaneously. And that a classical computer can't do. It has to go to one configuration at one point in time, next configuration, next configuration. A quantum computer can touch all these things at once And that's the magic sauce and really the only magic ingredient that makes a quantum computer so much more powerful. Touching many things at once in one step in time.
Is your question answered or is there a follow-up? Okay, no, it's just usually we have these situations like, yeah, you said that, but now I have a follow-up question. So always feel free. Don't forget, it's about you also. I mean, I love my questions, but hang on.
So nowadays you often hear about the quantum race. It's US or Europe and China and whatever. Is this really that competitive? Do you also feel that, or do you also sometimes run together? For example, or the superconducting quantum companies. I think you can also learn from each other.
Yeah. Obviously, it's for bringing about any new technology or new scientific insights. It's undoubtedly helpful if there's a community and you can exchange, look, I've done this, you publish it and you get feedback. And of course, the trade-off space, as we say, there's so many engineering choices that even a well-funded effort like Google's effort, we can try possibly everything. So there may be excellent ideas that we just didn't have the time to check it out. So therefore, community and competition is key. There's actually in business school truism that they tell you if you want to bring about a new technology, it's almost essential that there's some competition, because you can't possibly convince the world of doing something completely new on your own. So typically new things come in clusters. That's the cooperation part. But yes, I definitely feel that competition has increased. When we, in December last year, when we published our Willow results, at that time, many quantum startups were in danger of being delisted. Their stocks were worth 10 cents or 20 cents, and they have to be at least worth $1. Otherwise you get delisted. So many of the quantum startups were in danger of being delisted. And then we publish the Willow results and look, quantum error correction really works. It seems like there's no major obstacle anymore this is going to happen. And then overnight, these companies suddenly reach tens of billions of valuations. So of course, my team looks around and there's probably, if you all count it together, $1 trillion in value created. And of course, my engineers see this and say, like, I should have maybe been in one of those startups who have much worse technology and suddenly have huge valuations. And that's just the startup scene. Of course, large companies watch this and think, oh, it's really going to happen. What does this mean for my business? They get in the game. And because quantum computing has some applications in cryptography, well known, that are related to national security interests. That's why nation states get into the game, and they don't want to be the last to have a quantum computer. Also to support the industry. If you have a pharmaceutical industry in a country that does not have access to a large working quantum computer, you're in trouble. And I think places like China fully have realized that, and therefore it is a very heated environment where sort of best talent is in high demand. So all of you who study quantum computing, I think you have something to do.
Yeah, maybe a bit of a follow-up question to the previous one. So what's the policy of your lab in publishing not just the result, but also details of the techniques? So how much is basically like a business secret that you keep, and how much do you publish? What's the kind of the policy and the balance between the two?
Yeah, so this is, like in academia, I always joke, that there will never be an end to the discussion who should be the authors list on this paper. That's a favorite academic sport. with respect to publication policies, this is also constantly be renegotiated. There's not a final once and for all answer. Quantum computing has a strong academic DNA still because it's a new field. Industrial efforts are rather nascent. I mean, by now they're 10 years and more old, but still students, or it used to be until very recently, a PhD sport. So that the people in your lab were largely people with PhDs in physics, computer science, math, and they just expect that they can publish. They come fresh from academia, they are used to publishing, they want to continue publishing, and it's a detriment to attracting top talent, and sometimes that, hey, no, you can't publish here. We have competitors close to where I live in Malibu. There's, well, I shouldn't give concrete names, but there are other companies that don't let you publish at all, and they are sort of working highly secretive, where often the engineer doesn't know in the room next door what they are doing. It's highly compartmentalized. And guess what? These places have a hard time keeping their employees. If you can go over to Google and you do your work, and if you are a very good scientist, and early in your career, you want to let the world know, look what I have done. So there is a strong push from our team. They want to publish. And of course, publication, I don't have to tell you, I have this number of great advantages. First, I think only if you write it down, you really understand it yourself. You always invariably you think like you understood it all, no need to write it up. When you do, oh, wait a minute, what about that? So it makes things better. Second, you're committed to memory or institutional memory, so that in 5 years or 10 years, we can still look at it. And then as advantage is, of course, feedback. Somebody in the outside world sees it, agrees with it, builds on it, or disagrees with this and shows you how you were wrong. And of course, speed matters. So I rather publish something externally, it's sort of refuted or an error is spotted, versus holding an idea close to your chest. Oh, it's the greatest idea, and then you run with it for years until you realize it's not working well. So there's a huge value of publication. So big push from the employees, obvious value. But then there's a downside. When we published the 2019, we called it at the time quantum supremacy results, the first computation fast on a classical computer. 2 years later, there was a publication from China, and at first when I saw it, they used the same color tables, and I thought it was a made-up paper where they just took the data, but it was so similar, and anyway, I felt they used the same jokes. But then we found out this was actually work done. This experiment had happened, and it really set the clock. Okay, so that 2 years behind us, essentially. But this was clearly a warning shot that, oh wow, people are paying attention and they're close on our heels. And so we stopped. We still publish. There are certain areas where we love people to copy and build on it, like on the algorithm side. Look, we did this algorithm, and then we hope that people take it and do something similar with it, build on it, because that creates more market for quantum computers. But for the processors, if there are some tricks, like yesterday I showed you how coherence times get better by a factor of 2 pretty much every year over the last few years, that we can't tell anymore what it was, because it's sometimes too easy to reproduce once you realize what the idea was. So we have clamped down on publishing such key elements that are enabling to a competitor. It's a shame from an academic perspective, but it's a necessity if you want to succeed commercially.
Yeah, I understand. Because like reproducibility for us as in academia, that's kind of one of the most important things when you publish. But I also understand that in a company, and you invest, I can imagine, quite some big sums into this research. You also want to keep some advantage at least for 2 years or also.
Yeah, would we have much chance to have you pass it on? Okay.
So what do you think the reason is that a similar publicity boom like AI is receiving in the last couple of years has not happened for quantum computing in the same way? So it's always been around and people have been talking about quantum computing and how it is important and it's going to make an impact, but it's never reached the same level of public awareness or hype. Is this just down to the harder explanation of how it works or the smaller promises of what it might do, or what reasons could you imagine? And also, would you want this to happen in a similar way, or are you happy that you get to do your research relatively in silence and work among people that actually care a lot about this and not the sort of dumb public that only muddies the waters?
Okay, so yeah, there are also a few questions wrapped into one. If I had a drawing, I can describe it. I think it's just a question. AI as well as quantum computing are exponential technologies, so they're often referred to exponential, where sort of the by some metric the achievements what these technologies can do grow exponentially. And AI is just much older, actually. I'm just writing an essay, working title is but actually so I'm thinking it's maybe this is handy, but this question I still try to answer just verbally. So yeah, I'm writing a little essay. Working title is Quantum plus AI equals Quantum AI. And it looks at the relationship of AI to quantum and vice versa. And for this essay, I looked up a little bit the history and reminded myself that the AI is about at least 25 years older. So if you pack, Alan Turing wrote his imitation game paper in 1950. Certain elements like neural networks, the McCulloch-Pitts neuron goes even back further, 1943. While the, I think, important presentation by Richard Feynman on hey, nature is not classical, damn it, and if you want to simulate a natural system, you better make it quantum mechanical. I think this important insight, which gave birth to the concept of a quantum computer, that was 1975, so this is 25 years later. And then, but both, so that's what I wanted to draw, essentially, of both these exponential curves. So AI is right now in the very steep part, and like it's this breathless race where every day something amazing new happens, where even experts have a hard time predicting out further than 3 years what is going or not going to happen. And quantum for the longest time was just a game in the lab. It was also exponential, but in the beginning exponentials tend to be like very slow, and then to the external world nothing has happened. Oh, you went from your qubit from 1 to 2 qubits, 3 qubits, and then the error rates got a little bit better. Nobody but experts in the field would be interested in. And now we're starting to see, oh, there's at least something that classical computers can do. That's cool. So general audience starts to pay attention. Oh, you have quantum echoes, the first useful algorithm. Not that useful yet, what can I do with it? But it's going to change. So I think it's just this offset in time that explains it. And yeah, stop here, I think.
You make me do sports.
How about we have one more microphone?
Yeah, I was thinking that too, but otherwise sports is okay.
Thank you. I can borrow this one, but I know it's...
One argument of the quantum skeptic was up to recently about the hardware, and I think you have a very good answer to that. But as far as I understood, another argument was that maybe the time that the application becomes quantum, there will be some better application on classical computers. And it feels like there is this very beautiful Shor algorithm with the prime decomposition where indeed, and we hear a lot about the application in cryptography, but where else do you see application that will not be, that might not be beaten beforehand by classical computers when the real stuff come into work?
Yeah, what you describe, sort of a boogeyman in our field or for quantum algorithm people, is what we call dequantization. You think, oh, look, yeah, it's this awesome algorithm, let's say, I compute the structure of this molecule, and there's no way you can ever do this with a classical machine. And then some smart chemists go out and show you otherwise. Say, I don't have to fully understand the whole molecule. I only go to an active space, as I call it, and then they reduce the problem and find symmetries. And before you know it, they answer the question about this molecule with classical methods. And then we quantum people are all sad. So this has happened a number of times, and this is going to happen again. But in quantum computing is pretty new field. See, the quantum echoes algorithm was invented over the last 2 years. This algorithm, I'm happy to explain it here again. I explained it yesterday in the Gödel lecture fairly extensively. I wanted to make people see why this one, we are fairly certain, will not be dequantized, because key reason is, your neighbor asked earlier the question, what's the magic ingredient that makes quantum computers better? Yeah, it's this working with superposition states and the evolution, so that you have these massive interference patterns where you have, which are hard, exponentially hard for classical computers to compute. And we could show, I think, to physicists, I think very convincingly, that the verifiable signal, to tie it all together, in the quantum echoes algorithm is constructed by a complex long loop interference, and that is not doable on classical machines, and therefore will be an algorithm, as far as I can tell, that classical people or classical algorithms will never do well. And this one example, there are others, some come with proofs. So there will be, I think, a growing nucleus of quantum algorithms where indeed the scaling difference is exponential, and it's not going to change by any smart trick.
I mean, I'm just really wondering now, what was this microphone for?
It's for the camera.
Okay. So I'm ready to do sports. I was just kidding before. I knew it. I scared you, didn't I?
You still have so many prepared questions.
I wanted to stay with the AI topic. I wanted to crawl there. So please, you do it for me.
I was just wondering if you are comparing HPC systems, then you have the pre-exascale systems, then you have exascale systems, and you're always comparing the same systems against each other, and they are better. This one system is better than the other. And if you want to compare a quantum computer, you need to prove that in eternity there is no computer that can ever solve this. Isn't that so unfair? Because you also build better quantum systems in the next couple of years. So, yes.
I think this is just sort of features of the early state of this field. I think very soon, or hopefully in a few years, we will see, let's say, for example, the quantum echoes algorithm explained this. Didn't explain it here in the last days, as a good application. It can be applied to learning structure of molecules from NMR data. And so hopefully this makes its way into the practice of NMR analysis, and then NMR practitioners who are not necessarily fans of quantum computing or don't like quantum computing for the sake of, oh, it's a cool new technology, but they have work to do. They want to understand features of molecules, and if they start to use quantum computers just because it's the better tool, even if then a classical supercomputer could have done it still in 3 months too, nobody will care for that anymore. Actually, we already reached this stage. We have this program we call the Hardware Residency Program, where we invite students from quantum computing groups all over the world. And if they have an interesting idea what they want to try on a quantum computer, and they can come and work with our scientists and engineers. They help them to get really the biggest oomph out of the existing chips. And they told us, for example, there were a group from TU Munich, they say it's the compute power that your quantum processors give us exceeds what we can access at our university. So in some ways, this is already a practical advantage that, yeah, if that person just can't get the classical compute power to simulate what the quantum computer is doing, hey, that is a very practical. I was very happy when I heard that. We will see more of this and these esoteric conversations. Is it 10 to the 25 years or is it only 10 to the 20 years? This will go by the wayside and people will just vote with their feet. And for certain problems, hopefully they will tap into a quantum computer. And for others, they will use a hybrid system, or this is probably the generic use, classical and with access to quantum together, and then sometimes classical, or many times classical machines will just be sufficient.
Following up on this line of thinking, I think is extremely interesting that we have problems that we built on which quantum computers are better than classical ones. But I guess the breakthrough would be to have existing problems that we already know classical computation struggles with, and then show the superiority of quantum computers on those kind of problems. And I wonder if there's any clear examples, for example, in cryptography, where you do get this advantage.
Yeah, so of course, a clear success would be like a quantum computer was instrumental in developing a new medicine to cure an important disease. That would be a clear-cut success. Or a quantum computer was involved in designing a nuclear fusion reactor such that you get a large Q energy out to energy in. These would be this. Or the quantum computer helps a poor person who lost their private key and can't access their Bitcoin wallet anymore. So I think these would be clear-cut examples of success. And yeah, I think we are going to see, again, chief optimist, I think we are going over the next 5 years see some of such examples.
Yeah, I have 2 questions, if I'm allowed. So the first one is, do you see any relation between the development regarding hardware in quantum computing and the classical computers? Because regarding the size and, of course, the error rate and so on, so there was also some development. So is there anything to learn from that, what was happening for classical computers, or this is completely different story? And the second question is maybe about where do you see the role of the university in this development to make breakthroughs? Because it seems that, of course, for such kind of breakthroughs, you need a lot of investments and so on, which universities usually don't have. So, but what do you think? What is the role of universities in this case here?
So, to your first question, of course, there will be many analogs happening in quantum computing, where, let's say, for example, I explained how for the superconducting modality, superconducting way to make quantum computers, there's currently the challenge that we have one wire per qubit, one wire per coupler. So that's an engineering abomination. If you want to build a 1 million qubit machine, you have 3 million wires. That's possible. So we can do that, but it's ugly, it's expensive, it's error prone, and this reminds me very much of the machines where the photos from the 50s, where actually, I don't know whether you know this, the word debugging literally came from when there was a bug sort of getting under the vacuum tubes and caused a short, so they had to go and pull the bugs out. That was debugging. And sometimes when I look at our machines, we are still in this debugging state. But there is, in my mind, little doubt that we will make this much more elegant. We'll eventually have cold control electronics that lives at the 4 Kelvin or 10 millikelvin stage. And then there will be just a few digital lines going down, and the qubits will be co-located with superconducting circuits that will make the control signals, and this will all become sort of much more compact. We've already calculated it. The fridges we have today, the dilution cryostats, if such technology, superconducting control electronic, would work, we can put 500,000 qubits in just one fridge. And we have a number of them already. So this will all get way more compact, way more robust, way cheaper. And that's, of course, the way technology goes. There's also, until very recently, nobody had really thought about any sophisticated computer architecture. So actually in our group 3 years ago, if you would have asked somebody, how will your milestone 6 look like? People literally thought about it in like one big sheet of silicon, like stitched together. It's called chiplet technology, out of smaller chips, and you tile a 1 million qubit array until you reach a stage where algorithm people working together with quantum error correction people really think this through. How do we want our qubits organized, and how should they be connected? And then you realize, in hindsight, very trivial stuff that classical people, of course, know. There's certain qubits should be more memory qubits. Other qubits are touched more often. They should be sort of your CPU part. And so you get this differentiated computer architecture, and there's probably a lot to be learned. And the wheel doesn't have to be reinvented in computing. We can use techniques that are already well established in classical computer architectures. Oh yeah, so sorry, I distracted myself. So yeah, your second question was about the role of universities, or can a player with access to less investment than large technology companies can offer? I explained earlier that the trade-off space is enormous. Like, for example, there's so many, I speak in the superconducting modality, I'm sure similar stories are true. Like, for example, there's this question of, we call it TLS, it stands for two-level system. And this is sort of detrimental, or the boogeyman of superconducting qubits. You have those loops, in our case, out of aluminum, or you can build it out of tantalum and niobium, and you essentially realize your superconducting qubits by whoever built a radio when they were a teenager. Some of you may be electrical engineers. So basically, it's an LC circuit, a harmonic oscillator. In fact, we make it a slightly unharmonic oscillator. That is really our electrical element, and that is the qubit. Or I should say, in the oscillator, we use the lowest energy state and the first excited energy state. We call them logical 0 and logical 1, and that's what represents our quantum information. That's the qubit. But there are sort of spurious dirt qubits in the environment. For example, there could be like an oxygen absorbed to the surface of the aluminum, and this can go into two states, and there you have a little qubit that you don't control. And these little qubits that we don't control, we call TLSs. But it's really, you can think of them as dirt qubits. And our sort of engineered qubits are surrounded by these dirt qubits. And they talk to them, they can couple to them. And then information leaks out. That's bad. So we need to get rid of these TLSs. Nobody fully understands where they come from. There's probably various schemes how they can come about. I mentioned one, like there's pretty literally rust, like a little bit of oxygen absorbed to your aluminum. But there are many other. There can be strains in the crystal structure of metals. There can be little deposits of other materials that touch your qubits. So there's so much to be understood and found out, and some of these studies don't necessarily require a huge amount of investment to make. So a smaller experimental physics institute could make very nice contributions to such questions.
Well, I go to the next question. Just so that I've said it, the word bug is coined by Grace Hopper, who worked on one of the first computers, Colossus. And she found this little creature. And just so that I also said it, from her is also the quote, "It's better to ask for forgiveness than for allowance."
Yes. That's a motto we use at Google a lot.
I would like to ask a follow-up question on yesterday's good lecture. So thank you much for the lecture. I'd like to ask a follow-up question to the third part, where you roughly explained that consciousness could arise due to quantum superposition. And I'm aware that this is a philosophical and a quantum biological question, even maybe. And as I've written my bachelor's thesis in quantum biology, I would like to directly ask you if you think that quantum computers could create consciousness someday.
Yeah, yesterday there was a gentleman in the audience who asked a similar question. I put a concrete conjecture forth that a conscious moment is implemented when a quantum mechanical superposition or a new quantum mechanical superposition forms. Again, this is conjecture. Conjecture is just a fancy word for you just believe it. I'm saying this because this can, of course, be wrong, but what I'm proud of is that this can be experimentally tested. Should this conjecture, modified version of it, turn out to be correct, then we would have to conclude, because superposition states don't only form in our quantum computers, and then, of course, that answers your question. Yes, and indeed, quantum chips would create conscious moments, but not just quantum chips. In this water here in front of me right now, superpositions form. They form in the inside of the sun. They form all around us. So we would essentially get to this panpsychist view of things, that we live, that the universe is essentially a conscious system. There are conscious systems all around us, and it's not a unique property of a human brain or the brain of higher mammals.
I'm here if anyone has. Yeah, wait. Oh.
I'd like to follow up on this. I guess you might be aware of largely philosophical research, philosophers who develop sort of metrics for consciousness, so like for units of consciousness, maybe not necessarily in full-on panpsychist view, but well, there's a whole spectrum of near-panpsychist ideas. Have you thought of how this your conjecture in the experiments involving superposition and consciousness could maybe contribute to defining or like refining or somehow shedding more light on this attempts at quantize a unit of consciousness or so, or create metrics of consciousness?
Yeah, there's my good friend and colleague, and actually I should have put more names on the slides yesterday. I put the papers up there. The entropy paper has a number of the co-workers. On one of the co-workers is Christoph Koch. I think he is the highest cited consciousness researcher, and he, together with Giulio Tononi, promote this metric. It's called the phi measure, the integrated information theory measure of consciousness. So they say we know how to compute the amount of consciousness that's in this glass of water, or would be in the cerebellum or in your cortex. And in principle, I agree with the ideas behind this measure. They call it phi. Because essentially, phi measures how strong a system hangs together, or vice versa, how difficult it is to split the system into at least two subsystems. And that sort of makes sense to me. See, if you want to have, let's say, a 4-bit experience, then I think you can't be a system that only consists of 1 bit. You would say you should consist at least of 4 bits. And if these bits are sort of separate, then I think you can have, let's say, two 2-bit experiences if you split it in the middle, but not an integrated 4-bit experience. That seems to be pretty obvious, and therefore I always thought phi as a basic idea we should use something like this. By the way, here's an interesting observation. There is, we seem to experience this phenomenological unity of consciousness. It seems to be, it hangs together. And there is in neurobiology, it's actually known as a binding problem. Actually, in my master's thesis, I worked on it. Like, we know, for example, if you see something, a face or an object, then and you look how it's represented, you find, for example, in the primary visual cortex, there will be cells that are very sensitive to little edges in certain orientations. So there's a whole bunch of neurons that represent features of the object you're looking at. But you are not aware of it. You realize, oh, there's a cat, or there's a face of my mother. It's bound together to a unitary percept. How does this happen if it's really represented in a distributed manner? And quantum entanglement, I would say, is the only binding agent we really know. Sorry? That works over distance, and I can try to poo-poo some of the alternatives that have been suggested, but I think entanglement is the only thing that we know of that really binds things together, and therefore should lead also to high phi. And there's actually an interesting connection, and I told Christoph, see, when we did this 2019 experiment, it was very key for us that also these circuits can't be split in two, because imagine you do a circuit with 53 qubits, but you have your gates arranged such that there's maybe a set of 23 qubits that talk to each other, and there's another set of 30 qubits that talk to each other. Now these are smaller, and no gate goes between those two parts of the circuit. Now it becomes much cheaper to simulate. Now you can use your tensor network methods. Again, these are the methods, the best known methods for simulating on classical machines quantum circuits. So rather than having the challenge of doing one 53 qubit circuit, you do one with 23, which actually you can do on your laptop. When you do another one on 30 qubits, you can also do that on your laptop. So that's not quantum supremacy. So we actually checked sort of what is the meanest cut, and that there was no, the circuits were designed that no easy cut, that not even approximately you can split our circuits. That was key to driving up the classical cost. So I said, look, Christoph, if you would compute the phi value for our circuits, you would conclude it has a very big, by design, it has a very high phi value, so it should be a very conscious system. That's upshot of that. So I think measures like phi will be useful, and I think are nicely complementing these quantum mechanisms that we conjecture underlie consciousness to quantify how rich was the experience.
I'm looking at you all. Okay, then I go back to my place. I knew it. I just don't like this. No, I just don't like the phase with sitting down and then standing up. So take.
I have a question. How do you envision quantum computing in the future? Is it possible that at someday we shoot a quantum computer in space? So because of the cold area that and quantum entanglement that helps with the computing, or how do you see that?
I mean, there seems to be this innate tendency in nature that systems that process information become more and more potent in doing so. I mean, there are these ideas of phase as a singularity, and if you read Ray Kurzweil's book, like how systems, if you go back millions of years and you look how and take an information processing lens, then you see that, let's say, take life forms that early one single cell organisms, of course, have much less capacity for processing information in multicellular systems, and you have something like a brain, and then eventually brains join to societies, and they use tools to do more information processing. Initially, those tools are very primitive. They get more and more sophisticated, they get larger, and already now it's sort of like data centers are growing. I mean, it's not, I think, of course, many things can go wrong along this path, but it's not completely crazy to then just look at this and say, okay, can only be that long until we build the first Dyson spheres around our star to harvest the maximum possible energy that we need to do yet fancier information processing, and then we move out, or wherever is there, then move out to the next stars to harvest even more energy. So that is a not implausible prediction how the future could be. And because we know that quantum algorithms have advantages in certain cases, and we believe, yet to be fully shown, that quantum computing will be quite helpful for many important tasks. Actually, the latter we also pretty much know. So quantum computing will be in the mix, and along with classical computing resources will eventually start a journey into space. I mean, conjecturing that is, I think, not that far-fetched.
I'm looking at the audience. I would love to quote the thing that was also in the Einstein about this, since you mentioned space, a little satellite with quantum, but I didn't read through it, so it wouldn't a very educated story I'd tell you now. But what you said before, I thought it was very interesting, like this double-edged sword. Do you want to have an hype like AI has or LLMs have right now, or is it better to like, oh my God, please leave me alone in my space? But a third thing I think is also interesting, what can we learn from the AI hype for quantum, for example, and how could it perhaps also contribute? Because many discussions with AI right now also resolve around how is the data produced, how much water is needed to cool down all these big data centers, etc. Like the price that comes with AI. Do you think or expect or know quantum computing to amplify these issues, or can it also mitigate some of them? Could it?
And so, and this is a multifaceted question. So when people say, "Oh, there's so much hype around AI," I think this is probably the wrong word. I learned a nicer term. There's Mohammed El-Arian, economist that I have a privilege to talk to in person once a year, and he called it rational exuberance when he watches the investments that happen into AI, because it's not that it's not complete hype. I mean, probably all of you use AI every day, so that's pretty real. I mean, any important email I write, I have Gemini check it and improve, and so in a lot of work as a scientist you can't efficiently do can do it as efficiently if you don't use AI tools. So definitely this will be an important technology that most of humankind wants to use every day, and there is enormous revenue to be made. So it's not crazy to invest in there. But then he pointed out, as always, when new technologies like this happen, let's say this happened when the railroad came about, when airplanes happened, when the internet happened, of course, too many people rush in and say, "Oh, I want to be part of this too, And part of this is a great thing that creates the capital and investments that these new technologies need. And some of them will be unlucky and hold the bag. And when eventually it turns out there was an overcapacity built, we don't need that many railroad lines, or this railroad line is not used. Similar stories you will be able to tell maybe with some data centers for some period of time. So rational exuberance, I think, better word than hype. On quantum, if we deliver and do useful things, there will also be, or I would say, on the tail of AI, there is already rational, maybe slightly less founded still, exuberance happening. Quantum computing, I mentioned it earlier, how many startups have like eye-watering valuations, and just literally overnight. Personally, I enjoy, as a day-to-day work, go into areas long before they become obvious to everyone that they're important. I did AI since the 90s, or I did self-driving cars for my PhD thesis, so there are many areas I'd like to, or as I started thing like mobile visual search. Like in 2003, I wrote a patent that says, let's say you take a picture with your phone, you send it to a data center, and their neural network analyzes it and gives you information about this picture. And then you can use this information for something. This was in 2003. So now I learned that Google Lens, which I helped build, was initially called Google Goggles. Google Lens today, so mobile visual search, is the second most used search engine after Google text search itself. And in 2003, nobody cared for that. So I personally, right now it's consciousness. People look, oh my God, how embarrassing! It's interested in consciousness, and well, let's see. In 10 years, I think you already can see it now that people are asking those questions. Hey, are large LLMs conscious? So this question is coming up. So I love to identify areas early on that to me seem obvious that they will be important at some point, and then work in there before the whole world is there. So that's just a personal preference. So I like to be there in the pre-rational exuberance eras.
I wanted to ask you what a moonshot project will be, but I think I changed that question to, what if quantum really gets this big attention from the world? Then this must be for you the moment where you say like, okay, now I have to find a new field because now it's all over the place? And where would you go then now with your experience? Would it be the space then? I know one billionaire who would be very happy to have someone like you in his team.
Yeah, I mean, of course, just because something becomes more popular doesn't take away the scientific interest in it. I think quantum computing is a beautiful field and sort of helping design new algorithms that take advantage of superposition. And as you could tell from conversations of the last days, I really want to know whether this conjecture formulated regarding consciousness is correct or not. So I want to do those experiments and see is it correct.
So one of my jobs is also to always tap on my phone to see where we are in time. We do have 10 minutes left if someone has a question still. You met many people. You met almost many people.
Very prolific asking questions. I love it.
He's reliable. And also you have...
No, I mean the whole audience.
So I guess so far we talked about the positive aspects of quantum computing. I guess it will also become a disruptive technology for our current security systems, for example. And at least with AI, it was clear that institutions weren't prepared. It happened, we realized that we didn't know how to deal with it, so now we struggle to cope. And I see that quantum computing could have a way bigger disruptive effect if it becomes a thing, especially for bank details, etc. Do you think that institutions are preparing well enough, or are they thinking about alternatives on how to cope eventually, if?
I would say if we look at us humans, aren't we all to some extent procrastinators, where we start acting on challenges too late? Take something like climate change. I mean, we are not doing enough. It's happening and it's obvious, yet people deny it. I don't have to deal with it because I will be dead by the time it's really bad, and we don't do enough. And that is true for many other areas of technology, and with the effects or the implications of quantum computing to cryptography. The Google Quantum AI team often points this out, that it is high time to move to post-quantum cryptography if you want to have your information stay safe. And Google actually already did work in this direction. Actually, other teams, not our team, have moved to post-quantum crypto. We are doing tests with it. I actually should know better where exactly it stands, but definitely Google is doing this transition. And I know that, for example, in the US, the State Department, when they communicate to the embassies, this has been post-quantum since a long time. So they know this and they are prepared. And yeah, I hope your bank doesn't procrastinate too much either.
So as a last question is if people or if students come to you and talk about specialization, where in the field would you recommend to specialize? Would it be ML? Would it be theory? What would your suggestion be if they say okay, if I want to plan my career in this field, where are people needed, or where is much more research needed, and where should one go?
Yeah, the standard answer I give to this question, no, you should first and foremost go where your passions lie, what you're interested in, because just going somewhere in a field and you're not really interested in, just because you feel this will be important, this will be a miserable life. Just go where you have fun and you're excited, and it's something will come up. I mean, looking at what AI will be very good at first, I think if there is, robotic hands are still pretty clumsy. So if I think an experimental physicist who has to do something in the lab, their jobs are safer than a theorist who just has to think about the next algorithm, which the competition from AI there will be stronger. So if you, in our lab, we have sort of, pertains to other things, like, for example, can you work from home or not? You know, then I always say there are the people who touch the bits and there are the people who touch the atoms, and slightly different rules apply. If you are only touching the bits, it's easier for you to work from home. If you touch the atoms, you better come into the lab and touch them there. So, yeah, if you happen to be excited about something where you don't have to only touch bits, but only have to touch atoms, I think that's a better career direction.
So then, thank you very much for having taken your time. If you have a last-minute question, I think the way from here to the door is 1.5 minutes, so you have to be
our escape route
to run fast. But is there a way when someone would be like, "Oh my God, I have a question in career decision," like Google you?
Sorry,
No, contact. When I want to write you an email, for example, I can Google you, and then
it was a bit slow.
There's always
yes,
a follow-up question the next day you have, and I don't want to.
I'm terrible though answering because I'm so bombarded with emails. But nevertheless, it's Neven at Google.
Okay. So thank you very much. I hope you join us. There's a pretzel outside, I saw, so maybe you join us for a pretzel still. But thank you so much for having taken your time.
Thank you. That was a very nice.